When we think of enzymes, we often think of images like this, in which the enzyme is a big purple blob with an active site, and these little blobs that are the reactants go inside the active site, make the enzyme substrate complex, and then are released in the form of products. While it's a useful schematic, it oversimplifies things. Enzymes actually look more like this: crazy tangled chain of amino acids strung up together. Enzymes are proteins, after all. And while this diagram is designed to show the shapes that the amino acids make in a chain, if you zoomed in even further, you'd see this: tons and tons of atoms. And without all these atoms staying in just the right spot, the substrate would not be able to fit in the active site of an enzyme. So this raises a question: in what conditions do the atoms actually stay put and keep their shape? And in what conditions do they fail to do so? There are two conditions that affect this the most: temperature and pH. These factors must be at the perfect level for the atoms to stay put, otherwise they might fall apart. We call that perfect temperature or pH optimal, fancy word for the best, in order for the enzyme to keep its shape. So how could something like temperature affect the shape of enzymes? You may already know that when something is at a high temperature, the molecules inside it are moving very quickly, whereas when it's at a low temperature, the molecules inside it are moving very slowly. For example, the molecules in this hot thermometer are bouncing around so much inside their tube that they actually push their neighbors upward, whereas in this colder thermometer, the molecules are moving around a lot less, and so they chill out near the bottom. Well, the same thing happens to an enzyme. If an enzyme is at a really low temperature, then the individual atoms inside that enzyme are staying put in one spot, and so the overall enzyme keeps its shape, including its active site, and the enzyme is better able to act on the substrate. However, take that same enzyme and put it into a very hot solution, and it's in trouble. The individual atoms start vibrating inside this molecule, so much so that rather than being wound up on itself perfectly like this, it unwinds into its long polypeptide chain. And since it no longer has an active site, it's definitely no longer able to speed up chemical reactions. The fancy word for an enzyme that has fallen apart is denatured. Denatured enzymes lose their shape and then can't speed up chemical reactions anymore. It's worth noting that while high temperatures are always bad for enzymes, if temperatures get really low, enzymes can function, but they do function very slowly. While the enzyme usually keeps its shape, it and the reactants that it acts on are moving very slowly. So if they are, it takes a long time for them to get into the active site, for the enzyme to change shape and induce a change, and for the products to be released. So the enzyme speeds up the chemical reaction a bit, but not as much as it would at a normal temperature. So as shown in this graph of a human enzyme, at very low temperatures, the rate of reaction is low because the molecules are moving slowly. But as it warms up, the enzyme does a good job at speeding up the reaction until it gets to its optimum temperature of 37 degrees Celsius, which is our body temperature. But as the temperature gets beyond that, the enzymes start to denature and fall apart, and so they can't speed up the reaction as much, and so the rate of the reaction goes back down again. Okay, that was temperature. How about pH? The other factor that affects enzymes. For that matter, what is pH? Simply put, pH is the acidity of a substance, or how acidic something is. When a solution is acidic, such as the contents of your stomach, it means that floating around in your stomach are a bunch of hydrogen ions, hydrogen atoms that have lost their electrons and become positive. If you compared that solution to a glass of water, the water contains far fewer hydrogen protons. It's mostly water molecules in here, but there's a lot more H+ in the solution in the stomach, and so that's what makes it acidic. Water, therefore, has an average pH, a pH of 7, while acidic solutions like our stomach have a lower pH, in the case of the stomach, a pH of 2. So how would this affect an enzyme? Like, let's say you're eating a piece of fruit, and the piece of fruit comes down this way, through the esophagus and into your stomach, and that piece of plant has enzymes that the plant was using to run photosynthesis or something. What's going to happen to those enzymes? Bloop! Now it's suddenly surrounded by many positively charged particles that it's not used to. Each of those particles is going to exert a magnetic pull on different atoms inside the enzyme until the enzyme denatures. Of course, then the enzyme will do a terrible job at speeding up chemical reactions, and that piece of plant is going to be dead as a doornail. The moral of the story is abnormal pHs cause enzymes to denature. The same occurs in solutions with high pH, but for the opposite reason. Windex has very few hydrogen protons in it. It's the opposite of an acid. It's actually called a base. Because its pH is well above 7, it's actually got a pH of 11 or more. So if an enzyme gets sprayed with some of this stuff, it's surrounded by way fewer of these positive charges than it's used to. And without that moderate amount of H+, it also denatures. Now, different enzymes have different optimal pHs. For example, this enzyme pepsin, which works in the stomach, actually has an optimal pH that's pretty low, like around a pH of 2, which is where the stomach is at, and then it denatures at any lower or any higher than that. Whereas trypsin is an enzyme that functions in other parts of the body that at a closer to neutral pH of 7, whereas if it got as acidic as pepsin could withstand, it would definitely denature. To conclude, enzymes lose their function when they lose their form or shape. And that happens when either the temperature or the pH is not optimal. At those suboptimal temperatures and pHs, enzymes denature and don't speed up chemical reactions. Whereas at optimal temperatures and pHs, they keep their shape and speed them up.